Does everybody have a link to this? Let me see. Uh, that I'm going to send in chat here. Everybody have that? If you go to that link, you'll see that there is a link that I'm pointing at right now, the one that I just highlighted. You have to download that file, and that folder is this one. It's called basic example. Okay, you can store it wherever. Now, not only are the Python codes in there, you also have essentially all the result files also. Okay, and we'll go through each of them as we run each of these codes. But the reason why you need to be able to run this yourself is because, at the end there's going to be an exam, and you're going to have to generate information by yourself that you will not necessarily have the help. Okay, so every file, every output file, everything, even the final result file is actually in this folder. Okay, now who does not have? Now I don't want everybody to tell me whether they have access to the folder, but just tell me who does not have this folder, and you can put it in anywhere. Make sure you unzip it though. Anybody does not have access to that folder? Okay. All right. So everybody has access to the folder. So first thing I want you guys to do is go to the files and drag and drop, or just go to open files and drag and drop this file called buildprofile.python. Okay, go and drag and drop that file, and that's what we're going to start with. Now, once we start running that program, if anybody has any issues, they will be able to, we'll be able to figure it out. Okay. Okay. Everybody is in the same place now. You've got that build_profile.python file in the script part of your Python. And so what we want to do is you want to hit this button here. Okay, you want to hit this button here which says run. Alternatively, you can also hit F5 on your computers. I don't know what the Mac people will do, and that program should run without a problem. As soon as we run that program, I'll tell you exactly what that code does. Okay, who didn't get it to run? No? Everybody got the program to run? Your result should look kind of like this. The program that you just ran, okay, and we can look at various things. So first let's look at the web page. And what we are going to do now is we are going to look only at the basic tutorial. Okay, the basic tutorial. And what the basic tutorial does is it takes a protein whose structure is not known, and we'll see what that is, and we will then mount it on a similar protein whose structure is known. Okay, we're going to mount it as use the protein whose structure we know as a scaffold. So what we did when we ran the build profile is, let me show you something. Okay, so and this is and when it comes to the protein that you're going to model, there are now all these complications, and every year they come up with new things to account for the complexity. So if you were doing this as a research project and it's part of your research, then you would really delve really deep into the various options. But with this basic example, you should be able to communicate this to be able to solve the basic simple structures, right? So whatever you're learning today will be sufficient for you to create the model. However, unlike in the case of Arpita's situation where you can't get anything to work, we have to get these things to work. Okay, so anybody who has a problem then we can work with me one on one. Okay, so what are we doing right now? So let's go to this file. Okay, so this file is also sent to you. Every file you ever need is in the folder. Okay, and you'll see that this is something called as TVLDH, and TVLDH is the protein whose structure is not known. Okay, and TVLDH is the abbreviation for Trichomonas vaginalis. Okay, it's a it's a so the Trichomonas vaginalis is the, I think it's a fungus, and or a bacterium. I think it's a fungus, and one of the proteins in that genome, so that's the species Trichomonas vaginalis, and one of the proteins there, an enzyme, lactate dehydrogenase, was was is used. Okay, so that in this exercise, that is the protein that we are going to work with. Okay, and okay, so that is the protein we're going to work with. Now, that is the sequence. Now, if you look at that sequence, it's written in the FASTA format. It's not really the FASTA format. It's almost like it's called an alignment format, and that file that we're looking at, and you guys can open it too, is TVLDH, Trichomonas vaginalis. L is lactate dehydrogenase. That's the file, and you'll see that this is what is called an ALI file or an aligned file. It's very, very important for us to look at this file. Now, if you look at this file, you'll realize that it resembles kind of like a FASTA formatted file. Okay, so let me go through this. So this is just the P1 and just the name of the file, and remember the FASTA format. Anything related to the caret is this. Now, is not really processed, okay, but it is for information. Now, in a FASTA formatted file, you'll first get this line with the caret and then all the information related to it, and then you'll go straight into the structure. In an alignment file, or called ALI file, as you can see, it's in the basic underscore example folder. You'll find that it is called, there is another file, there is another line in between the first line and the line related to the sequence. Okay, and so that is, so for example, that is the sequence file. Now, when you say sequence file, it is the file that of the protein whose structure is not known, and your job and our job today is to get through and find and create a structure for this protein. Now, it says it's a sequence because it's unknown sequence, right? If it was the known, it would be the similar file for that would be called structure X. Structure X. But let's not worry about that right now. That's a little downstream, which we're going to finish today. So that tells you the name of the file, and all these things in the middle, these colons with no spaces in them. If this was a real structure and it came from the PDB file, from an actual PDB file, from a crystal actual X-ray or NMR crystal structure solution, this information here that I'm highlighting with the cursor would be full of information related to the structure solution. Okay, so we'll come to that alignment file later. So this is the file. Now, this has to be written in the FASTA format, which means 80 characters, and the last one has to be an asterisk. That basically tells Modeler, the software, that this is the end of the sequence. Okay, very, very important once you begin to deal with, right now it's okay, but when you begin to deal with unknown files, that is when you're going to have to be really sure that everything is lined up correctly. Any questions for the input file? Any questions related to the input file? So this is the sequence. Now what you guys should do is, you know, again, the eventual aim is to create a structure for an unknown, for the create a structure for a protein whose structure is not known, and that's going to be your job. So make sure you have an archived file so you kind of don't mess around with the sequences or the Python codes too much. Okay, so we are starting out with this. We are starting out with this sequence. We are going to, at the end of it, we're going to come up with a structure for it, and we are going to use the methodology that is listed in this program. Okay, so now, so that is the TVLDH alignment file, and again, and you can see it's exactly the same style as the file that you have in your folder. Okay, so what is the point of a build profile? Okay, now for that we need to look at the PIR file. That's about 4 megabytes. So we can look at that file. Let's go to that file, and also let's begin to understand first what is this program doing. We have an unknown sequence that was the tvldh.ali file, and then what you're going to do is you're going to say, well, I have this unknown file. Now I've got to send it through a bunch of other proteins and do a sequence alignment. Now you guys, you know, even the students who are taking this class for the first time know what is a sequence alignment, right? You're going to try and do an alignment with a bunch of known sequences to find one where, you know, that there is a sequential alignment, not a structural alignment, because a structural alignment is what we are going to do, but we're going to look for a sequence alignment. So what the PIR file does, is kind of something with 95% similarity. That file, and we can look at the web page again. So we have that file. Now we are going to look for this pdb95.pir file, and PIR format stands for Protein Information Resource. Now let's look at that PIR file. Okay, so if you look at the PIR file, it's a big long file. It has lots of proteins in it. So notice it's written in that same ALI format. It's the ALI format, right? Now the C here means it's a comment. Okay, in the ALI formatted file, a C is the C semicolon is a and you'll see there are many sequences in here. So think of this almost like when you do a blast search, you take your protein or your DNA sequence and send it through, and then it goes and does a sequence alignment with some sort of a big archive that GenBank has, and then it comes and gives you all the results. So basically what we are doing in the build profile is that we're taking our unknown sequence and we're running it past all of these files, all of these protein structures. Okay, we're going through all of these protein structures to find an alignment, a file that is aligned. Now, these are written in the same alignment file. Remember how I told you that in the TVLDH file there were only a bunch of colons? So here you'll have a whole bunch of additional information. The colons are separated by additional information, which says, you know, it goes from it has a chain A, for example, and it goes from amino acid 1 to amino acid 166, and you know, it tells you a little bit more about the protein. But this is the part that's the most important. It tells you what the PDB ID is, and that's why to begin this class, you know, the last class that we had for this particular subtopic in this curriculum is that's why we went through that structure, you know, we went through that structure lecture and looked at the PDB file. Okay, so this is the PDB ID that is of crucial importance. And so what our program is doing is it's doing the equivalent of a blast. It's taking the sequence we don't know, and again I'm repeating myself because I want some of this information to be cemented in your minds, and that is we're taking the unknown in that format and we are now going to find a bunch. It does not have to be one perfect, but we're going to have to find a bunch of proteins to which there is very strong similarity. And the build profile did that. Okay, now the result of the build profile, shows up. So again, we ran it through this file, we did the alignment file, and it wrote the output to something called as build profile.prf. Now you can, again, all these files are available for you, and so let's go to the build profile.prf, and that is that file. Okay, and if you look at our web page, you'll find that the results are here. Okay, this is the build profile code which you just ran, and you'll see that here are the results. Okay, so this is almost like and you have all of this, right? So here are the results that you get. Okay, and what the build profile program did was it went through the files, it went through each of those proteins, did a sequence alignment, but we know we want to do a sequence alignment with those files because the end result is going to be, okay, it aligns well with those particular proteins, but more importantly, we have the PDB entry, which means we know the structure of these files. Okay, and so you almost can see, you know, if I show you here, you can almost see in the last column, it's almost like an E value, right? And we remember at the end of a blast search, what is the expectation value? The expectation value is a measure of the randomness, or strictly speaking, the non-randomness of this error. So you can see in the first column, and you know, you can look at each of these, you know, you can look at each of this. It tells you exactly what it means. You know, 95% similarity. It tells you what part of the protein aligned with what part of the protein. You know, like if it's a big protein, whether how much of it aligned. All these numbers are explained here. Okay, all of that information is explained here, and this is kind of like an E value. So it went through the build profile process, went through all these files, and identified things that are in the first column. And that same file, you can see here. Okay, it did the same thing. So I can actually highlight in Notepad 2, I can actually highlight an actual column. So it went and it found a bunch of information here, and you know, E values and things like that. And more importantly, that was a truncated version of the file. You can see if you open the build profile.prf file, you'll see that it actually aligns. It shows you the nature of the alignment, right? And remember in that, you know, the alignment is never like, oh, at amino acid number 1 to amino acid number last aligns with amino acid number 1 to amino acid number, the last amino acid in the protein's whose structure is known. So what you'll see here is that it doesn't align to the exact start to the end of protein. So, but it might align to a big protein, but it might start somewhere in the middle. And you can see, for example, in the case that I'm highlighting here, it doesn't align to the immediate one, right? Then also, just like you would do with a blast or a typical alignment, a sequence alignment, you see that, and we understand this, right? It adds gaps. It has all kinds of interesting things, gaps. It makes it align. So when you have a template file, and to that you want to add an unknown file, the software does a lot of energetic adjustments to account for things like gaps and everything. Okay, so you'll see large paths, and it found I don't know, 30. It found 30 of these of the top of residue, sorry, the proteins, and these are the PDB IDs. It found that it aligned well. Okay, so let's go back to our web page and follow our alignment. And now what you're doing is you then looked at these alignments and you found the 6 best ones. Okay, you found the 6 best ones. Now in the exam situation, you're going to have to make that determination as to which are the best. Now let's go back to this file and kind of keep this at the back of our mind. So we have 1 BDM, 5 MDH, 1 B8P, 1 CIV, 7MDH1SMK, these PDBs. So we'll see exactly why these were selected, right? So BDM, okay, so it basically said that anything with zero, okay, anything with zero, that means just metaphysical improbability of that alignment being in random, it just found the ones with zero. Okay, so you can see it found the TVLDH is always going to be zero because that's our original, that is our that's our original unknown, right? Then the next one with zero is B8P, B8P, then BDM, then we have MDH, and right, 5 MDH and 7 MDH. Now, what does A mean? A mean that you remember in our PDB we could have A, chain B, etc. So A means that it aligned with the chain, it aligned with the chain A, not with the chain B. Okay, because and the reason why you want to specify A versus B is because if it, in the case of a homodimer of a protein, you will actually find, you know, A and B are the same with some small changes. But in a heterodimeric case, the chain A will be completely different from chain B, etc. Okay, so but for example here, if I scroll up, you'll find that A5Z, it just was the whole protein. There was no, there were no, you know, there was no dimeric component to it. Okay, and so that's highlighted here. Here's another one, but the other ones, and you know, three of these, for example, but you'll see that the ones where it aligned with chain A, it aligned with chain A. So we took the 6 where the E values were 0, but even if you look at these other E values, you know, they're not bad. They're actually pretty good. Okay, so but you took the ones with the 0. Now, so that was, you took your unknown protein, your the protein whose structure is not known, and you ran it against everything that is clustered around 95% similarity. Okay, and you when I say 95% similarity, that PDB 95 dot underscore 95 dot PIR, it means that it's going to be like anything less than 95% similarity. What do I mean by that? It means that, let's say, the whole protein data bank, there's one protein that's really easy to crystallize, really easy to crystallize. In fact, when you buy a big crystallography machine costing, you know, $700,000, in order to do the alignment, in order to configure that machine with a protein crystal that's easy to crystallize, you use a protein called chicken lysozyme. Okay, and so chicken lysozyme, it crystallizes like within minutes, so you can always put that and use it to configure your machine. Because it's so easy to crystallize, so many PDB entries are of chicken lysozyme. Okay, just one mutation here, one mutation there. So let's say, why don't I download the entire PDB? Well, downloading the entire PDB means you're going to get so many of the exact same protein. So 95% means that it's 95% unique. Okay, 95% unique. So some which are just, you know, many crystal versions of the exact same protein are ignored in this. So they want to remain relatively unique. I'm actually working with one of our students, Sarah Metwali, and we are trying to do some statistical analysis on sequences. And so what we've been doing is but just to make sure that we are on solid ground, we've been identifying clusters which are just 20% unique, 40% unique, 75% unique, 95% unique, just to make sure that, you know, that our statistics are on solid ground. Okay. So what we have identified is these are the ones with 0. Okay, so they will say these are the 6 top alignments, or the best alignment possible. Now what we have to do is we have to choose one. In this particular exercise, you choose one. In some situations, you might choose more than one. Okay, so you choose the 6 top ones, and you say, now I want to find among them which one is the best. So you're actually going to literally do a kind of like a phylogenetic analysis of the 6 top ones that you chose, right? And that then takes us to the new script. Okay, that takes us to the new script, and that is compare.py. Okay, and again, you also have that script, so feel free to drag and drop that script into your Python code. Now, before we continue, are there any questions? I kind of belabored some things. I repeated some things so much that it might be, kind of a little bit boring, but I want to make sure that it stayed in your mind. The software doesn't exclude it. The people who created that P underscore 95, so this question comes from Mir, and how does it does this, so basically what it does is PDB actually does it also. So if you say I want to download a bunch uh, of proteins, it tells you what kind of uniqueness you need, and you can specify that. There is another software developed by Roland Dunbrack from the Fox Chase Cancer Center, who started as a faculty there when I started as a postdoc there. He has created a software where you can actually specify exactly the percentage you want. So PDB actually will do that for you. It will allow you to download with a certain amount of specificity. Modeler doesn't do it, okay? So Modeler doesn't do it like right now in the build profile process. What they do is they probably every time they have a new version, and now if you have Modeler, and if you have, because you use Modeler to create a link, so when it sends you it's registered your email. So every year, once a year, they're going to send you an email saying, hey, a new version of Modeler is available. So that new version of Modeler will come with the same package, like in the basic example, etc. And they are going to have a kind of a PDB underscore 95.pir that will contain the new 95% uniqueness set of sequences. That makes sense? So this software doesn't do it. So if you do a multiple sequence alignment, and then you can essentially throw it out. So PDB actually does that for you and allows you to download it. Does that answer your question, Mir? If we don't know the structure, let me read your question. You said several things at the same time. If we don't know the structure and have no leads, can we use these type of basic sequences to help us build a relatable sequence? Well, if you have no, that's a good point, right? So that's a good point. So if you have no, it's like, for example, the olfactory receptors, which we work on, okay, which is part of my research, uh, that that software, that those proteins, there is no related structure, okay. But what we understand is that there is a very distant structural relationship, not a sequential relationship, with rhodopsin. Rhodopsin is a protein that's found in the eye, okay, and there is a structural relationship, but the sequence relationship is not very good. So in that case, what we do is we use that, and then we determine some things like, using some the helical regions, and then these helical regions separately, and then match the helical regions together. So there are different ways in which you can do it. And the methodology that you're talking about is kind of using pieces of it to kind of build a relatable sequence, is called threading. Okay, it's not homology modeling. I mean, it uses the foundations of homology modeling, but the principle is called as threading. And so sometimes what you might do is there's a reason why this build profile tells you, what part of what number to what number aligns with what number to what number. Let's say you have a protein, and and half of it has a structure that's very similar to one protein, okay, or a sequential similarity, and another part of your unknown protein has a sequence similarity to another protein. Then what you can do is then you can line up, when we come to the final part of the piece that's creating the alignment files, we can line up several proteins which are bits and pieces, right, of what we understand to be the structure, and then we put dashes where it comes to the rest. So this way what happens is you can kind of create some sort of a chimera. Now, Remember, if you're going to create these chimera of regions that are very small, then your randomness, that is your e-value, increases. Okay, and as your e-value increases, just like in a blast search, that means the higher e-value is bad. You're looking for something that is identifiable without any randomness to it. There are different ways. There are different ways in which you can put it together, and then what you do is you leverage the really cool things of template and known structure. You leverage modular, but the key is how do you create that alignment with a structural region. Okay, so that's kind of the key. So as you go deeper and deeper into it, you'll get it. But right now we're just, this basic example is something that gets you started, and then if it becomes part of a research project, then you look at the more of the subtleties, the nuances of the different things that you can do. If you can look at even in your basic example folder, you'll realize that there are many different things that it does, like loops and things like that. Okay, and each of these is a file that even here, for example, you can actually look at a advanced. So this is the alignment, and you can actually you can even look at. You can't necessarily find it here, but along with the basic HTML file, you'll also get a lot of advanced stuff also. Okay, so that's something you can do. They also have, for example, a way in which you can do it over the web. But I'd rather you begin to understand the foundations of it, so otherwise it becomes a bit of a black box. Okay. All right. So now we got the top five, and then now we're looking at our compare. Um, we're looking at our compare.py file, and here you'll see that already built into it are, it's looking for the alignment. And remember, these are all, you don't have to mess with it, don't edit it, don't change it. As I said, create an archive version of it, that if you ever need to do something, you can, and you kind of mess something up. But if those of us who have been doing the advanced bioinformatics, you'll realize that you'll realize that the syntax, etc., are basically formatting. So for example, if you look at the for PDB in chain, and those of us who are doing the advanced class, you understand that even this colon here in the indentation, the indentings, etc., are all part of a typical Python program. Okay, so the scripts are written in Python, but the background information is kind of like when we were doing BioPython, right? So this is a uh, kind of an adaptation of Python in order to be able to run modular using the Python scripts. Okay, it used to be a scripting program, but now they use Python for the scripts. And you'll see what they have done is they've already created this file for you, where they have said, here are the protein names, okay, that you chose, and these are the ones in the build profile. They had e-values of 0. Okay, and like, as I said, don't worry about each of this. Each of these is like, this is a modular, and each of these are now, these modular things that do something. Okay, don't worry about how the program is written. But so let's do this. Let's run the code. Okay, and it runs pretty quickly, so all of us, let's run the code. And if you run the code, you'll see that you get something like this. Okay, you get something like this. So if you recognize what this is, it's kind of like a phylogenetic tree. Okay, and if we go to our text file, you'll see that the compare log file, and you can open that file like I'm doing right now. the compare log file has something very similar, is that it created a, so for example, it creates this matrix of comparisons and similarities, and you know, for example here, and then here it gives you a phylogenetic analysis, much like it gave you a phylogenetic analysis here. It's the exact same one, okay, with some slight differences because it's much easier to see. It's much easier to see in a text file. So you see all these. You see these are um, structures. You look at the similarities, see the CIV and the 7MD are the closest. The one SMK is a little further away, uh, you know, and then these are clustered kind of together. But there's something else that's also being considered, right? If you want to create a the best model that you're capable of. Remember, this is an unknown protein, and we're using the models, this kind of like the templates or the scaffolds of known proteins. So if you're going to create a, you know, you're using one protein to create the other, wouldn't it be nice to get the best structure? So in addition, not only that, to the closeness of each of these, we are also looking at what is called as a resolution. Okay, and we talked about resolution, how good is your structure resolved, and the better the resolution, the more precisely you can determine your atomic positions. Okay, so that's what compare.py do. Okay, well, what do we do with compare.py? This is the compare.py. You just ran it. Now, anybody have any problems running it? Anybody? I mean, if it ran without a problem and you got that phylogenetic tree looking thing, then you're good. Otherwise, let me know before we continue. Done. And so now we have a dendrogram. Like as I said, it looks kind of a dendritic analysis, like a phylogenetic tree that's being created. And this is the result that you get. And that's exactly the result that you got in here. Okay. Now this thing gives you a little bit of additional information, but right now we're good. So now let's look at the comparison, right? Look at how do they decide? And this is something for you to decide, because you're going to have an unknown protein. You're going to run it up against some sort of a sequence, and you're going to have to make a decision as to which one is the best. Okay? So now let's look at their explanations. And for their explanations, we look at this example. So we can see that CIV and 7MD are almost identical, okay, both sequentially and structurally. However, 7MDH has a better crystallographic resolution. Remember, the smaller the number as far as resolution is concerned, the better it is. So if these are exactly the same, if this one and this guy are exactly the same, but this is better resolved, which means you have a greater precision in terms of placing these in terms of the atomic positions. And to be honest, between 2.4 and 2.8, we are not talking about a big difference, but hey, you go with the one that's better. So what we're going to do is we're going to reject that guy. Okay, we're going to reject that one. So that's what they say. So eliminate CIVA. There's a second group of structures, 5MDH, BDM, 1BDM, and 1B8P. That's these guys. Okay, that's these guys. Uh, and but 5MDH has the poorest resolution, 2.4, so we can knock that guy out. Okay, and then the one SMK is the one which is the least precise because it has nothing in common. It's the most diverse of everything, so we can throw those guys out, right? And so the lower sequence identity, I don't see the 34%, but let's just take their word for it. To the query sequence. SMK is the most diverse, and somewhere it says it has a lower sequence similarity, and so it could be somewhere here, but it's not listed correctly. So let's just take their word for it, and so we throw that one out because it's the lowest identity. Then we finally pick one BDM because it has a better R factor. What is this R factor? And we talked about R factor. R factor is, remember, when an X-ray produces your experimental data, all it is a bunch of electron clouds, just this areas of density. You then have to use software, and with the knowledge of what the sequence of the thing you're going to solve is, you're going to actually place it based on that. And that's why there are sometimes you'll find big sections that are missing, especially at the N terminus and the C termini. So that how well your the model that you created fits the actual experimental data, the clouds, is called a goodness of fit, okay? Or it's called the R value. And the R value in this case is 16.9, so you're just going to take, because now even the sequence identity is really good, but it's only 45%. Okay, so because of that, this guy is the winner, 1 BDMA. Okay, so that's the process, that's the way you do the process of elimination. Okay, it's a combination of many things, and very often they say that actual structural modeling is a science as well as an art. Okay, how do you decide which to choose? How do you decide, like this thing right now, what you guys are going to rely on is the alignment that's been tried and tested, because that's always been the basic example. But in reality, when you're doing a research and thing, and you really have just, you're completely flying blind, that's when you say, well, the software put a gap here. Is that necessarily the right place for the gap? In that case, what you're going to do is you're going to play around with how the structure file aligns with the unknowns file, and you're going to move things around and kind of mess around with things just until you go. Now, so the question is, why will you do that? Because in addition to just relying on the software to do it, you also begin to think and say, well, this is a protein whose structure you want to solve. Its structure is not known. You want to create a model of that protein. So then you begin to ask yourself, well, what do you know more about the protein that you can contextualize information about it that is not available purely by just the computational act of alignment. Okay, so you know more about it, and you might say, well, maybe this gap, maybe this loop needs to be a little longer, maybe the boundary between this loop and the helix is a little too constrained based on how they did the alignment. I want to relax the edges a little bit. So these are decisions that you make based on, therefore it's kind of an art and a science. Arpita, you actually have a very excellent question, and that is, what is a good R value? Now, if you were doing small organic molecules, okay, then like a 1%, a small organic molecule, right? Then even a 1%, even a 1% um, is not good. Okay, it has to be less than 1%. The alignment between the density, because these are small molecules. But remember, at the end of it, even when you stick a protein into the X-ray beam, it's a very viable thing. It's obviously a huge thing, and every time you add atoms into the mix, you're going to get something that is the variabilities are going to increase, your errors are going to increase. So I would say anything between 15 and 20, 15 and 20% R value, the fit between your model that you're kind of drawing over the kind of the smear density that you find, would be good. Okay, 15 to 20. Now for minerals, it would be like 0.1%, which has to be like bang, bang, bang. Everything has to be in the right place. For organic molecules, you can potentially, zero point 0.5, 0.8 fit, or or percent fit is considered good. So that was a very good question. But in case of a protein, because it's huge, the error rates just kind of magnify based on the flexibility of the protein. The density that you get out of it is really smeared. Sometimes you might have one atom, but the density is so big that you're really not sure exactly where that atom is positioned, and then that's when you're going to get all these errors. But 16.9 is actually is very good, okay, for a protein. 15 and 20 is good. Sometimes you'll have people who will publish even worse, because it's really poorly behaved, but but if to get a crystal structure is actually a pretty big deal. Sometimes they're career making, just to be able to solve one crystal structure fully. Okay, and some of the best scientists in this field are the ones who kind of make it a habit of always doing the right thing. When when once when I was a postdoc and I barely knew anything, I was learning about biochemistry from a book called Proteins for Dummies, and I'm not exaggerating this. This is not a joke. This is real. Um, I attended a talk by this guy at I think he was at Rockefeller University, if I'm not mistaken, or Rochester, one of those two upstate New York ones. And he came and he gave a talk, and he was, very popular with his. He was a good scientist, trained at Harvard, the postdoc, and he was, and so when he told us this really interesting anecdote. He said that when he told somebody that he wanted to, as part of his research profile, he wanted to do, protein crystallography. Somebody turned around to him and said, "Do you have the soul of a riverboat gambler?" Okay, so in fact, my entire first postdoc had, other than the time I started developing my bioinformatics skills, my programming skills, I was in a lab that did crystal structure, and to the entire time, we never got a single protein purified, let alone crystallized and found a structure. So there was, in the 2.5 years that I was there before that lab closed down, there was an X-ray machine worth $650,000, and it sat there without a single crystal being mounted on it, just simply because we just could not get the proteins to work, and we couldn't. So there's a lot going on as far as that is concerned. Okay, now everybody ran the compare. So now again, the final outcome is that this one BDMA is the winner. Okay, but if you look at your folder, you'll see that they've given you the protein PDB files for every one of these. Okay, so if you wanted to say, I want to just try something different and see exactly how differently the structure is going to show up, right? How differently it's going to show up. Then you can, in the next part, in the Align 2D program that we're going to run, you will find, you could use another one. Look at the third file that we have now. So here's what's going on. Does water molecule affect the R value? Water molecules are picked up. Okay, water molecules are picked up in a crystal structure, but what happens is they have a very specific signature. The density is a very specific signature, and people, yes, because I mean, your protein, the crystal that you put there, is actually in buffer. Okay, and water is the big part of the buffer. And so what you see here is there are water molecules will necessarily show up, and because the hydrogen atom has almost no density, and its density is captured towards the oxygen atom, typically in a PDB file you're only going to see oxygen atoms, and they're going to be called het atom, while the regular amino acid atoms are going to be called ATOM. You'll see way down at the bottom of a PDB file, you'll find something called het atom. And het atom will typically be heteroatoms, which are non-protein atoms, and those are going to be, one of them will be water molecules, or if you find a metal or calcium, or an earth metal or an alkali metal, that's part of the protein. Very often you're going to find copper and zinc and things like that, but that's typically called a het atom. Okay, but it doesn't affect the R value, because what happens is you're building your model over the density of the protein, and therefore you know exactly which are the water molecules, and you know how to avoid them anyway. Okay, all right, very good questions. So let us keep going, and now we come to the aligning with the template. Okay, so now what has happened is we sent our software to find the best alignment with our unknown protein, sequential alignments. Okay, then we took the sequential alignments and we did a structure sequence comparison between the top 6 that we chose. Then we took those things, and then based on a combination of things, closeness, sequence similarity, based on resolution, based on closeness, we actually made a decision as to which one's going to be our template. Okay, you could potentially take all six and make a template out of all six, but you found the one that is of interest. The PDB file is one BDM. Now remember, when you do your unknown for the exam, make sure you just don't mess around with the code, but put the ones that you want just exactly in the same spaces, okay? And once again, I've said this many times, make sure you have an kind of like a pure version of your codes, then you can just move that you can move over in case something kind of messes up. Okay, so it's going to create what is called a PIR file, which is the alignment file, and something called as a PAP file, and we'll see what those are presently. Okay, so if you want to go into your code, you'll find that you are going to go to this next code, and that is align2d.py. And again, that has also been created for you. Okay, that has been created for you. So the environment file, you see the file is going to be BDM. Now remember, when it's identified a PDB for you, make sure that you've downloaded that PDB. Okay, you have to download that PDB, because now what has happened is, yes, it's identified everything based on sequence, structure, and things like that, but what you're really interested in now is that scaffold, right? That's what you need. So in order for that to happen, you need to have the PDB. So in a real life situation, an exam situation, let's say it identifies, you then have to go to the protein data bank, download that PDB, and keep it in the exact same folder, and then edit these lines to reflect that PDB file. Okay, so what do we have to align? We have this. Okay, that's a PD then, which comes from the bdm.pdb. So once you say bdm A, is going to know exactly that it's going to only take the A chain, and then your file is tvldh.ali, which is a file that we looked at first. Okay, so that is the file we looked at. Let me find it. That was the file that we looked at first. Okay, and so we have all those files, and it's going to create an alignment file, and that alignment file will be tvldh bdma align file. Okay, and it's going to create, so now it's going to create an alignment file. So now what you want to do is align 2D, that is a 2D alignment. Okay, that is because it's now going to align it, and then that's the file you can modify. For the current situation, we're not going to modify because it's already kind of done into the ground. So everybody take your align 2D py and run it. Okay, so I'm going to hit the thing, and it's done. It doesn't take that long. So once everybody's, let me know if anybody has any troubles running this align2d.py. And let's go back to our web. So when you align it, let's see, what is it going to run as? You're going to get a whole bunch of things that look like this. Okay, so it's basically done the alignment, and offsets and gaps and all of these things are done. And so now let's go to our web and see what it's done. So now it created a tvldh1bdma align file and a tvldh1bdma pap file. So let's see what that alignment file looks like. Okay, this is the pap file. And let's look at the alignment file first. So you see, we started out with that tvldh alignment file. We started out with that, and you'll see that here is the structure X, that's the BDMA file, right? And it wrote it in that same kind of FASTA looking thing, where now you have all this information, name, and you can see that it's an enzyme because it's got the enzyme nomenclature. And information, it goes from 0 to 318 amino acids. Now it's 318. Now it actually did the alignment. Okay, so this is the alignment file. Now if you look at this alignment file, this is your unknown. Okay, this is where the program becomes really unforgiving. If you don't specify something correctly, if there's no chain, if your PDB is not in place. So if you look at this asterisk file, this asterisk, if I just hit low, if I kind of hit the down button arrow, see, it's aligned. You see the cursor? It's behind that star, right? So now what has happened, it's aligned the one that it's the template with the structure, and wherever necessary, it has put gaps. Okay, it's put gaps in the file, but at the end of those gaps, you realize that the gaps have to align with amino acids exactly. Okay, exactly to the point that, okay, you'll see everything has to align such that these two asterisks are exactly one below the other. Okay, so the total number of entities you have after you put gaps on both sides, whether it's the one with the structure or the one with the sequence, has to be exactly the same. And you might say, well, did it just put gaps in the known? No, it actually has also put gaps in the, it also at least put one gap in our unknown protein. Let's say, for example, you decide that you really want the best features of 5 different structures to go into your model. Now you have the control over it. So then you would call structure X 1 BDMA, 7 BDMA, 5 BDMA, that 1 CIV, that SMK, all of those files you would write into your aligned file, so it would create one below the other. In which case, what it's going to do is it's going to take many of these template files and put them into many of these template files, and each of those template files are going to contribute towards the final structure. So you can do that also. Okay, you're not really necessarily stuck with one. So remember how I said that if you have a protein that's really big and half of it is aligned with one structure, known structure, and the other half is aligned with the next known structure. So then you could also almost say, well, this part is aligned with this protein, but then what you would do is you would count like from here, which would be about here, and here you would have only gaps, because we don't want this remaining part of the structure to contribute to the protein. Then you would have a second template here, and you would say anything from here on should be blank, should be gaps, and I only want the sequences from here. So this way, and because you gave it the PDB file, it would know in the creation of this model exactly which amino acids have to be taken from which PDB. But whatever you do, it all has to align, as you can see the cursor, such that whether you put 10,000 of these and you have to put gaps, it all has to begin and end at the exact same spot. Now if you look at it right now, you feel like the asterisks are not aligned, but they actually are, right? And I've shown you this many times. And the reason because when I used to do this in the beginning, it used to drive me crazy. It's like, wait a minute, why is it not, why is it giving me so many errors? And you're like, I don't even know what those errors are supposed to mean. And then you kind of painstakingly go through each step and try to do these fixes. So one of the quickest fixes is to make sure you have the PDB sitting in the folder that you need, and the second one, you have to make sure that the protein starts and ends at the same place, which means you know that if you add gaps, you have to add compensatory gaps around it. Okay, so that was the aligned 2D. Now let's look at the PAP file. Okay, so the PAP file is, so the PAP file, and you're looking at it right now, is a text file. Okay, It has a different extension like PAP, PIR, etc., because they are all. I should unpause. All right, sorry. So, Olva Bimisola, the PAP file is a text file, just like the PIR file. They're all text files, right? So, I always like people to add this thing called Notepad to Notepad plus plus, which is always a really cool file, and I'll show you what I mean. It's called Notepad, but it's Notepad, which is so much better. I'm showing you right now. I'm actually writing a code in another language, Perl, and this is a research project that I'm doing with one of our students, Sahiti, who's actually um, one of the interdisciplinary studies program. So download this Notepad++. It's free. You can you can let me see what I can do here just for a second here. So even for example, if it has a Python code, see, I'm opening the Python code and it's coloring it effectively. So I can literally, it's not like when you say Notepad, it's not just a better version of Notepad. Okay, but if you don't have this, now Notepad++ is completely free. I've been using it for a long time. So it knows how to color things for, it's not necessarily the idle code, which is the editor for Python, but it is also, for example, this is an XML file that I'm processing, and then there is a Perl program, which what happened to it? I just deleted it, I think. But all of these are text files. Now, if you don't have Notepad++, certainly I would recommend that you get it. I mean, there are many editors, really good fancy ones. You don't have to stick with Notepad, with this regular Notepad. But if you right click on your file and it says how to open, just say open with Notepad, and then click on, like, there's a little checkbox which says click on it for if you want every file like this to be opened in Notepad, and your program will know. And so it's just a text file. Okay, but what happens is sometimes these files become entry into other software, right? For example, what you're seeing here is, if you looked at the alignment file, the ALI file, you'll see that it all got written as almost like a FASTA format, right? And I've basically said this like 2,000 times. So I'm going to, if you look at the PAP file, however, it will tell you exactly what is aligned with what, exactly where are the gaps. For example, here's a gap in the BDMA file, here's another gap. Where are these gaps? How are they lined up with each other, etc. Right? So this will tell you more specifically. That's called the PAP, and it's a PAP. It's called a formatted file. It'll also have numbers. This is 210th amino acid, etc. Okay. Um, Now this goes up to 318, the BDMA file, but and if you look at the alignment file, it says up to 318. But I think because of all the gaps that you've added in here, it kind of extends, this sequence extends beyond 318. Okay. Any questions beyond that? Okay. All right. So now let's go back to our web file, and let's go to our tutorial. And so now you have the PAP file, which tells you the alignment. Now basically you have the last step, and the last step is to build a model. Okay, you've done the alignment. Now this is the real big thing, right? Because you've aligned everything, and the reason why the PAP file is aligned in this way is because you know exactly how an R should be aligned with K. Now, if you look at the stars here, the asterisks, you'll realize that the asterisks are only if the if the sequences that are being compared are the amino acids are identical. See, everywhere else they aren't. So for example, this is an asparagine, this is the histidine. So you're trying to do the best you can, right? It's not like, oh, it's 100% match and therefore this is not an issue at all, right? So and you can get a kind of a snapshot view of the nature of the identity just by looking at the number of stars, right? And you can also see, for example, that as you go towards the C terminus, right, the C termini, you'll realize in the C termini that the identity gets weaker and weaker. There are some segments, for example, here where the identity is really strong, right? Here, for example, is really strong, in which case creating a structure as a template is not going to be a big deal, right? You just kind of mount one on top of the other. But for example, here you have really poor, you have really poor, uh, in this area, you have really poor, alignment, right? Really poor. This area and this area. But you still have to do the best you can. And that's why a computational model at the end of it is a computational model. There's not much you can do with it. But, now, but on the other hand, for example, you'll see we're not just talking about sequence identity, we're also looking at sequence similarity. So for example, here you might have something that's, and I'm not saying that it's all perfect. It's remember how I said there's no protein that comes with gaps. There is no protein in nature which comes with nothing, right? There is always, there is never a gap. The gap is our way of rationalizing two things to kind of cluster them into some sort of a frame of reference of equality, so we can say, oh, they are the same, and if they have the same sequence and if they have the same structure, then they might belong, and they belong to the same family. Maybe they have the same maybe they have the same function, or a very similar function, right? Now the whole notion of the blossom versus the PAM matrix, in terms of what was used to determine those that pairwise numbers, okay, the log odd ratio, and some of you, the people who are, I think Manisha, Raksha, are actually taking the methods in bioinformatics class simultaneously, and so they are more familiar. The rest of you are likely to have forgotten, but it's premised on the same notion that when you look at similarities, when you look at the log or the ratios which tell you what, for example, a cysteine and a cysteine is a high number, that means that particular residue is highly conserved. You either take things that are varied, or they belong to the same family or belong to different families, and you can come up with these numbers. Okay, and so that's what the PAB, it also gives you a picture. It says, well, is this really good? Now remember that one which was, this is 45% similarity, which means 55% of the amino acids here are different. Okay, and that's very critical. So it's very likely that you can keep searching, you can try different things, just because something is, there might be some big uncertainties, and there might be some big uncertainties in this region, there might be some big uncertainties in this region, because there's similar, like for example, here there is an arginine, sorry, a lysine, and here there's an aspartic acid, and a lysine and an aspartic acid are from a standpoint of their function, because one is acidic and the other is highly acidic, highly basic. But from a structural standpoint, it's possible that they both have these dangly long side chains, and there might be that structural similarity. Okay, and once again, you would never do this. You would never do this in a kind of in a research setting. You would, because you've been studying this protein for long and understand the protein, you might do some other things related to that protein. And I mean, once we are done, towards the end of this class, not this class, but the end of this particular section of 4 lectures, I will show you some of my research in this area. Okay, and you can see how far we can take it, and I'll give you a little bit of a perfunctory before we get to the final movie, which I will show you. Okay, all right, any questions related to this before we get to the final code? So we have the PDB, we have the structure of the known, and then we have exactly which, in terms of the template, which amino acid will line up with which amino acid. So for this we have a structure, for this we don't, right? So we're going to superpose one over the other, and then there are these there are these big gap areas where nothing seems to work, in which case what we're likely going to do is we're going to or the program is going to take that information, and it's going to do some extensions, play around with some energetics in order for it to work. Okay, so this is I mean, this thing that was developed by Andrei Shali, and by the way, the way it's pronounced is Andrzej. Okay, it's a Hungarian name, and it's Andzrej, and the pronunciation is Andrei Shali. Okay, and so this guy was the only one to come up with this idea, and all of protein modeling is only possible. There has not been anybody who's come up with anything better. There is a commercial version of this which goes into software that the pharmaceutical companies with tons of dollars use, and some of the money that he uses from that, some of the money that he gets from that endeavor is then poured into. That's why we can avail of this for free. Okay, and that's why if you try to register using a Gmail or a Yahoo or a Hotmail account, it's not going to let you. Okay, that's why you need an academic account, because it's very, there's always that fear that somebody might do a lot of malfeasance with it. Okay, at some point we started out with 20. We've lost somebody. I'm trying to see who we lost. There's two Moids, that's fine. Alright, fine, whatever. So the last code that we're going to run is the actual modeling code. Okay, and that is the model single.py. Now remember, this is theoretical, this is computational, and this is related to energetics. Okay, this is purely related to energetics, and when we come to the protein ligand docking part, then we'll talk a little bit about this whole notion of a global, and I'll give you a more of a qualitative view of what is, if you look at the energetic landscape, the energy landscape of a particular interaction, what does it mean to be in a local minimum or a global minimum and things like that. Okay, so that's for one or two lectures from now. Okay, so there's nothing much you can do. You don't have to put the PDB, etc., because that's all in place. And then your known, for example, has to match your, for example, we look at this, the known is BDMA, TVLDH. You have to make sure that it lines with your text, right? And the text, the PAP file, also the ALI file. So remember, this is one BDMA, and this is TVLDH. Error would occur, for example, if you had one name here, or you forgot that A, and then your model file didn't have the BDMA. Okay, so that's when all kinds of problems occur. Okay, now this is going to take a little bit of time, depending upon the speed of your, because what it's going to do, and remember, there's a reason why I started this sub discussion by talking about this being about energetics. It's a highly theoretical notion. Okay, what it's going to do is it's going to give you, if you look at this part, and don't worry about this part, you, as long as you have your alignment files and things like that, this part is going to be about how many models do you need. So, the typical question would be, well, why do I need many? I need one model, right? But that's not how we do things, right? Because what we are doing is, because it's energetic, just because it's going to calculate the overall energy of one model, and then the overall energy of another model, and it's going to rank them 1, 2, 3, 4, 5 in order of best energy, or smallest energy, or the most stable to the, but remember, this is a model, so the most energetically uh, the best energy or the lowest energy does not necessarily mean it's going to be the best model. Okay, so let's uh, let's run it. There's nothing else to it. It's we have the alignment, everything we aligned. We're happy with the alignment. We let the software do most of it. We could also potentially have done some of this by hand, which is what some of my students who have done. And there's a student 4 years ago who did a lot of work on taste receptors, and eventually we took those receptors and we went to the visualization lab people, and what they did was they created a uh, what is that thing where you put the glasses, kind of virtual, kind of a virtual reality, and you it was amazing. I put those virtual reality glasses on, and it was like I was in the lab and I was surrounded by the faculty and four of his students, and I put on those virtual reality glasses, and it uh, everything vanished. I was in this room which was gray, and the five, six people around me, or this big lab around me, it all vanished. And then some of these receptor proteins that one of my students developed, that was there, and I could use these gloves with that haptic feedback, and I could move, and I could take the entire protein model and put it around me, so I could actually be inside the protein, and I was looking at the internal surface of the protein. It was out there because but it all started with exactly what you guys are learning, and then we I presented it at a international conference in Italy, of course virtual, so I didn't get to travel, but it was fascinating, and it was not only well received, but people were like, have you tried to sell this to a pharmaceutical company? But all in academic research, so that's destined to die in poverty, so to speak. So, but anyway, so I wish, then, because everybody got busy, I wanted to put that whole thing in YouTube videos that I could demonstrate it. But there's some other things that I've done that I will demonstrate for you at some point later. Okay, we are ready to run the software. There's nothing else other than like this is a typical Python formatted code, and the make part is the part that runs it. And we said, now if you wanted to make life a little easier, you could go in there and you could change it and say, I just want two models, in which case it'll run faster, but let's just go with five. Okay, so you hit enter, and it's going to take I mean, it might take a little while, not that long, but it's the part that takes the longest, because it's churning through everything now, right? It's aligning all the files. You could potentially give it 1 to 100, and for the night, and then you'll come back and it'll have calculated. Uh, oh, Shraddha's missing. Okay, wondering what happened. So if you guys are running the code, then it's also running at the same time. Okay, my code has run. Tell me, your code. So you can see this is what we see. That B9999001.pdb, and its scored is dope. Score is dope is a is a kind of a process, and you can see the energy, right? Negative energy, negative 37543. So it's It's ranked in terms of lowest to high energy 5, and again, as I said, you could give it 1 to 100, and it'd still be okay. Okay, now you guys have to tell me for whom is this just running, still running. Now again, mine's a fast computer, mine's a fast desktop. My dopes, yeah, different because the energetics are not necessarily the same. They are based on, again, you're going to run the same code 3 times and you're going to get different dope scores. So they don't have to be the same as yours. The energetics in your situation might be slightly different, based on how quickly your program runs, how quickly it calculates interaction energies and things like that. Okay, so if you remember this, I'm going to run my code again, okay? And just to remember that number, just to see whether I have a different set of scores. So as my code is running right now. Whose things are not done yet? And you'll see now how I do this. I don't mean the Autodox tool so much. So we can actually do a visualization, and this came with the Autodoc installation. And of course, nothing would be complete without me. I'm going to add an existing. We already know it's CAM. So here I am. See? How cool is that? And this is just so as the protein gets now. So let's see who's not done. Anybody not done yet? Okay, so this is good. This is a lot less painful than I imagined. Okay, so if you downloaded Autodoc tools, okay, you would see something called as Autodoc tools here, and I've opened the window up. And there are many ways in which you can visualize your protein. But let's go back to our folder, and you'll see. So let's actually look at the code first. So in our folder, you'll see that, I mean, we just generated all these files. Okay, these are the files that we generated. Okay, and you can see from the date stamp it's today. Okay, you can see that it's from the date stamp it's today, which means we just ran it. But even if you had not run it, even if you had not run it today, the files are already available for you. Okay, so these are energetically the first 5 because we asked for 5, and these are some intermediate files. So just let's look at a file. Pretty much anything that ran here, okay, anything that you saw the thing scrolling up and down as a Sofec was doing the calculation got done there too. And so what I will do, however, is I'm going to open one of these files in my notepad. Okay, I'm going to open it in my notepad, and then we'll see in the text file what it looks like. And so you'll see that this is how the modeler runs, and it creates something very close to, it's a PDB file, right? So this is now the model that's been created, and they created a PDB file for the protein whose structure was not known. All right, thanks guys who texted me and said it's done. Looks like we are in good shape here. So, and even if it didn't get done for some reason, they already gave you the files that you're supposed to get. Now, but it's nice to run it and actually see it operate, because this way, in the time for the exam and things like that, you're not going to have a problem. So it actually created the PDB file. Uh, so that's pretty much what it did. Okay, so it created the PDB file. So we see the PDB file, and now let me go to the Autodoc tools. Okay, so you see the Autodoc tools are here, and so now in here into the Autodoc tools, Now this is what we will use as a visual for our docking process, okay? But that's not what we are interested in right now. We are interested in just using it as a visual. So I'm going to go to the docking program and I'm going to file. I'm trying to see Python script. You can't see what's going on, but you can go to file and is it import? No, it's read molecule. So I'm just going to go to the read molecule. So if you click on the thing, you'll get the read molecule, and then you have to kind of go to. So I would have to go to the basic examples, which for me is in downloads. Okay, I'm going to go to basic examples, and I'm going to open the TVLDH B9999001 file, and I'm going to open it as a PDB file, and there it is, right? So you can see there's my protein file. So this is the protein file that we created. Now, if you look at the rest of them, they're going to give you, variants on the same thing, but they're, for the most part, they're going to be the same. Well, now, what is the real value of this? Okay, so let's, while we're at it, we have a little time, and so let's play around with this. So if I click here and I open this, see, I'll get the entire set of amino acids. Okay, but so this is a great visual. You can do all kinds of things with it. So let me close it, hit a negative, that minus sign in a box, and let's look at the whole protein. Okay, so the whole protein is here, and you see that this, it'll actually, when I mouse over it, you're not going to see it, but it says display everything in line format. If I go on to the next one, it says display with ball and stick. So I can display with ball and stick, and then I can undo the first one, and it'll just show ball and stick. I can go to the third one and say display atomic spheres. So I can do more than one at the same time, right? I can then unclick one. So that's the spheres. And then if I want the amino acid, the secondary structure, I can click this, which is not showing up because it's under your surface. So I'm going to click that surface off, and you'll see, and you can left mouse over it, and you can see that this is our trichomonas vaginalis, and this is the secondary structure. So you see the helices, you see the strands. Now the really cool part about this is, what is the other one? This one says that you can display a molecular surface, which is a lot different than, for example, display the molecules. Okay, because the molecular surface will show you, docking regions. You see the docking region? So you need kind of, you actually, if something has going to interact with it, you need some space. And you can actually see this is a pretty big looking opening here, right? So docking will take place here likely. So again, it all depends upon, what kind of exposure the surface of the molecule has. And then you can also, you can label differently, and you can also change colors. And when you change colors, you can change by polarity. If I say change by polarity, okay, and I know David Goodsell. I actually met David Goodsell. It's a pretty nice guy. So this David Goodsell, if you see this guy, he's not just a good computational crystallographer. He's actually an artist. Okay, he's an artist. He's really, in fact, he had all these. He actually wrote a book once, and he had all these very interesting representations of molecules and proteins and things like that. So he's actually very good. So again, if I say all representation, I don't know whether how is this supposed to work, but I close it, but I don't know how this is supposed to work. So anyway, but here's the thing. If I go back to my stick representation and kill these other guys, let's say, for example, I just want some molecules to be shown as spheres or ball and stick or something like that, right? So if I open this out and the rest of it is stick, I say, let's say, do you see these two alanines, 12 and 13? I'm going to say I'm just going to represent the alanines 12 and 13 as surfaces. And did it happen? No. Okay, let me see what else. What if I represent them as ball and stick? So you can see the surface only works for the whole thing. See what I did is both the alanines here, so you can, in very specific ways change things. Okay, so again, this is one way to look at it, one way to modify things, and you can do some other, you can do all kinds of calculations, you can find hydrogen bonds, you can change colors by residue, things like that. Um, so you can do all kinds of things, but I just wanted to show you that the model that we set out to build is now built. Now, if you had problems installing Autodoc, the visual thing, or MGL tools, then you're not likely going to be able to test this out. So I'm going to actually close this class out now, but I wanted to make sure that we are on the same page, um, that the modeling part got done. And again, basic modeling is a good start. It's a good starting point, and then for research, you'll use various features if you need to, but it's always a good starting point to get some of the foundations out of the way. Having said that, I'll open it up for questions, and then we can go from there. You can send the questions in chat, or you can send your questions by or shout something out by unmuting. To overlay two proteins one over the other. Um, I think so. I think so. Let's go to read molecule, and then I'm just going to go to the one bdm.pdb, okay, because that's the one we use, right, to see exactly how close our, let me unclick this guy's, okay, actually let me open that one bdm.pdb. And here's your overlay, right? Now, because you have two of these, see, there's one BDM2, right? And let me open this and then, unclick two of these so it just looks. Now, one of the things that you can do, because it's kind of showing you this as it's showing up as different colors, um, you can then say, and remember why is this protein looking why is this protein looking so different from the other? Because remember how I told you there might be a homodimer or a heterodimer, and in terms of the homodimer or heterodimer, you'll see but we only aligned it with the A chain, right? And that's why that's the way it looks. So another thing that we can do is each of these we can do the helices, that'll kind of clean it up a little bit. So we'll do the helices for the model that we created, and we'll do the helices for the other thing that we created. Now wondering, and now you can play around, because off the top of my head I don't know how to color it, but here's your overlaying, right? And then let's take these parts out. Let's take these, let the ball and sticks out. So geez. So now we see how different, right? And you can see, for example, and again, scrolling or the middle mouse, you can see now this is one helix, here's the other helix. Now let's color this, let's color one or the other. I'd like to be able to do this by chain. Okay, see, so Jonathan, we can kind of start beginning to figure this out. So you'll see the pink guys are the BDM, right? And now let's make it smaller, and the TBLDH is the other. And now this other one, uh, so the pink one is the one that you just created, the one that you model you just created. This one is in white, and you can see, it's kind of the same, but everything seems to be shifted. The loops are the same, but they're not purely coincidental, right? And so, yeah. Does that answer your question, Jonathan? all kinds of things. Then you guys can play with it. I'm sure there's a YouTube video which shows you all the nuances of it. Now, even for example, here, while you have this in place, you can go and say, I want this. This not only do you can you do, like, let's say you want a ball and stick representation of this leucine 8. Okay, and where is the leucine 8? Can you see the ball and stick representation? And what we'll do is the ball and stick representation, we'll color it um, by instance. Now, I don't know whether that'll work. I don't know whether, okay, we'll make it small and see where it is. I don't think I can see it. Let's look for one. So anyway, you can play around with these all you want. You see how much the alignment is actually that's taken place. Let's see another ball and stick. Oh, there it is. There it is. See? You see the one I'm pointing at? That's where it is. Oh, like say atomic spheres. Yeah, that's where it'll show up. And the atomic spheres, and then we can potentially custom color it, or the molecule, not the molecule, sorry, the instance. So now we did the CPK coloring, and so you can see they're both coloring. So you can say, okay, which way does something point when it is, right? So you can do all kinds of things. Not only can you do it at this level, how you are doing zoom. Oh, zoom is the middle button, like the middle scroll button, right? So always remember, as a default, the left hand button is always the left hand button is the rotate, the middle is the zoom in zoom out, and the right hand is the translate. That's typical. Okay, so you can translate it up and down, back and forth, etc. So you can actually make some of these, not only can you do that, you can, if you open each of these, you can actually make specific atoms pop out in a different color. Okay, specific atoms. So there's all kinds of very interesting things you can do. And this is the Autodoc tools is something that we will use for our Autodoc tools is something we will use for our modeling. Okay, sorry, for our protein docking. So any other questions? The people who have not really been communicative. Okay, then what I'm going to do is I'm going to stop the recording, and then I'm going to share it. Take a little bit of editing. I might have to just sit down and play around with a little bit, but I'll share it with you guys. And I think this has been fun. It's worked out for everybody, I hope. This is the foundations of modeling. Okay, but and it's nice to take, so you can walk away from here with some really definable skills. And people who do computational work in terms of drug design and things like that, you guys use a more fancier version of it, which probably does a lot more fancy things. Um, Now, in terms of the docking, it becomes a little painstaking. Uh, about 4 years ago, a student of mine, two students of mine, and we were runners up in an international competition, and we were given software worth $130,000 to use for a year for free, and that software does docking in seconds. Okay, but it's not a bad idea, when it comes to free stuff, that you can. It's painstaking, but you begin to understand the nuances of how things are done.